Hey, welcome to Ones and Zeros. So, going to be doing our third episode in our Discovering an STM32 series. Can't talk properly. So, just following on from the stream we did a little bit earlier today where we looked at getting some of the GPIO code done so that we can more easily use the GPIOs. We're going to be following on getting some of the serial code done so that we can start looking at getting some serial data sent between the computer and our STM32 F769i discovery board. If you're new to this, it's the first episode that you've watched on this one, it might be worth going back and checking out the first two episodes. There's quite a bit of useful information there, as well as some information about some of what we're going to be looking at on our Twitch channel and YouTube channel moving forward, not only with the STM32 devices, but also with ESP32 and FPGA development. There will also be some Windows and Linux programming thrown in there as well. So just making sure everything is working correctly. Excellent. All right, so let's jump to this one. Wonderful. All right, so have tidied up a couple of little things in between the last stream and this one. The frame timing variables that we had set up as globals, I've moved those into our main function. So you can see those there. It makes this bit of code, the frame timing code, look a little bit neater, which I much prefer. And the code from the last stream is already up on GitHub as well. The code from this stream will also be going up on GitHub for free as well. So as I mentioned previously, some of the more advanced code that we start to look at, that will be available to Patreon members. So you can jump on Patreon to help support the Twitch and YouTube channel and help us to produce better videos, things like that, so that we can teach more cool stuff to people. So as I mentioned, basically just going to look at getting some serial code done today. So we're going to be using UART1 on the discovery board to communicate via the ST link to the computer so that we can pull up a serial terminal when that starts up. There we go. So that we'll be able to use it as a debugging tool, as well as what we're probably going to be looking at over the course of the next couple of episodes maybe, is actually getting sort of a console system or terminal system working so that we can actually set up some commands and be able to type in commands to manipulate things in a way that I find really quite flexible, so that we can just sort of add and remove commands and stuff really easily. And going to be using a bit of object-oriented stuff to be able to do that. All right, so let's jump into our drivers folder, and we can see the two GPIO files from the last stream. So we're going to create a new header file. This will be QAD UART.hpp, and we'll grab a CPP file as well. So QAD UART.cpp, like so. Let's get rid of that template code. We don't want that in there. And then we might just copy and paste this bit from our GPIO file into here. So we're going to use a few different classes to create the overall UART/serial driver. So we're going to, in the files we've just created, be basically building a bit of an interface to allow us to easily set up and access any one of the 6 different UART devices that are in the development board, so that we can basically reuse this class multiple times, whether we're transferring serial data to a computer or in between different development boards, things like that. This is something that we'll also be using once we look at implementing an ESP32, is basically providing the Wi-Fi and various other little features when we connect it up to the discovery board. So we'll be able to reuse this rather than having to look at modifying it again. So let me make sure I'm actually doing this correctly. Still getting used to this whole streaming thing. Find it a little bit of fun though, so. Alright, so make sure that we're not going to have any recursive inclusion, which we definitely don't want. And fix this one up, because this will be UART. Wonderful. Alright, that's all good. I believe it's still the 24th. That's a bit better. We might fix it up in here too. Obviously wasn't paying attention perfectly before. There we go. Alright. It's amazing the amount of things I've noticed that I miss that I normally wouldn't miss when I'm live streaming, just because I'm concentrating on that aspect of it as well. So first up in here, actually we might just put all of that right. UART.hpp. Alright, so we're going to copy that in here. Get rid of our thing there, and we're going to include QAD UART.hpp. Alright, so similar to what we did with the GPIO driver, we're going to look at doing a lot of the things moving forward, encapsulating things with classes using object-oriented programming. If it's done right, there's generally not a huge amount of memory or processing overhead, especially if we implement some things a little bit more C style, but leverage some of the more flexibility that you can get out of classes. So find it works well on these devices. As I mentioned on previous stream, most of the programming I've done for STM32 devices and development boards in general have been done with C programming language rather than C++, but I've been having a bit of fun lately doing some C++ stuff and seeing what we can do when we throw a bit of an object-oriented approach at it. So we're just creating an enum to allow us to identify which of the 6 UART devices we're actually wanting the class to set itself up with. We're also going to create ourselves a bit of an initialization structure. So just give that a name there. And also got another monitor set up now, so I got 3, which allows me to have some of my older code there to reference back to, which definitely makes this a little bit easier than it has been on the previous couple of streams. So first thing in our initialization structure will be which UART we're going to be initializing, and we'll be using the enum for that one. Chuck in a uint32, and that is going to be our baud rate. We want our IRQ priority. Also want the two GPIOs. So we're going to be storing the information in there for those. So, and we also want TXAF, so we know which alternate function to set up. RX GPIO, RX pin, and RX AF. Cool. All right. Now, this will be our actual class. Just add some comments in there just to help break it up a little bit. And let's create our class. Now we are going to want to create an enum. I might just call that peripheral state. Make that a UNAT. So this enum is going to help us track whether or not the initialization for the peripheral has actually succeeded. Whereas with the GPIO class that we created before, we did the actual peripheral initialization in the constructor of the class. We're actually going to do it slightly differently for this one because we've got a slightly more complex peripheral, and it's worth checking to make sure that things have actually initialized properly. So in order to do that, we're going to not be doing that in the constructor itself this time around. Now, let's just pop that in there. Now, let's pop one of those enums in there and call that m_estate. And what else do we want? So we're going to want to keep track of which peripheral we are working with. I'm going to may as well hang on to the baud rate as well, and our IRQ priority. Now we're going to keep the baud rate and IRQ priority stored in the class simply so that it gives us the ability to deinitialize the peripheral and then reinitialize it using the same class without having to instantiate a new class, just in case we want to do that. I'm a bit of a fan of sort of trying to make the tools I build as flexible as possible so that when I'm building other stuff on top of them, quite often I find that some of the features that I've thrown in there will actually come in really useful. So if I think I'm going to need it, generally it's worth throwing it in there just in case. So that will be TX GPIO, and we'll want to store our pin and our alternate function. And same thing for our RX pin. So there's going to be 4 classes that go into actually creating our overall serial device. So we're going to have this one, which is basically the one that's interacting directly with the peripheral. We will also have a FIFO class, which we're going to set up. So first in, first out buffer, which is, we're going to be using one of those for each the transmit and receive, just to sort of buffer the data. That way, essentially the approach we're going to be taking is using the interrupt handler for the peripheral to be able to help us to transmit and receive data without putting very much load or stress on the CPU and allow the CPU to do a bunch of other stuff instead. We also need to know which IRQ we're going to be using for this one. So we want an IRQ in type, and let's call that an EIRQ. Because that is also an enum. Now I'll just fix this one up as well. So typically when I'm naming these things inside the class, the M underscore denotes the fact that it's a member variable. The little e means it's an enum, lowercase u for unsigned integers. I'll put an I for signed integers, P for pointers, things like that. Again, just so that I can sort of spot what it actually is at a glance. We're going to want handle type def, so this will actually store the handle that the Hal wants whenever we are doing things with the peripheral after we've used the Hal to set it up. We aren't going to be using the Hal IRQ methods to transmit and receive data. We're actually going to be doing a bit of that manually, and as far as the actual transmit and receive, we will be directly accessing the transmit data register and receive data register for that instead. I find it just helps get some of the fluff of the Hal out of the way. As I mentioned previously, I'm a fan of using the Hal to help get things set up a little bit easier and get code written a little bit quicker, but I basically only use the bits of it that I want to use, and the rest of it I kind of just ignore. So let's get a constructor and destructor sorted out there. So much like we did with the GPIO driver classes, we are going to delete the default constructor. Not paying attention. Obviously wasn't paying attention there either. Awesome. Okay, so we'll delete that constructor. We're going to create another one, but this one we are going to be taking that will be UART init struct. So this will be taking a pointer. Actually, we might do a reference rather than a pointer for this one. And then we'll go through and do our member initializer list for this as well. So the state will be inactive when we first start up. And most of the rest of these are going to come from our structure that we've created. So this will be this one. That is going to be our baud rate. UIRQ priority. That one. TX. Also popped some foam underneath my microphone stand too, so hopefully you guys don't have to put up as much noise from me typing. I think a bit of it was traveling up through the mic stand, being a bit annoying there. So that will be that one. Again, that's coming from pinit. And that will be TX GPIO. TX GPIO, no, TX pin. Pinit, TX pin. TXAF. So we'll see how much of this serial thing will get done during this stream. It may be that we might finish it off in the next stream. But see how I'm feeling. I mean, this is my second stream for the day, so MURX pin P init RX pin U. This will be RXAF, and then we also need to get our for our IRQ. We're just going to chuck a default one in there for the moment, which will be UART1 IRQN. The reason why we're doing that, and we're going to modify that later, we're just setting it up that way for the constructor, is because if we jump into this file where we see all of our IRQs listed for this device, because they're an enum, we don't really have just a default one that we can throw in there, so we're just going to chuck UART1 in there for the moment, and that way when we actually go to initialize the peripheral, if we're doing a different one than UART1, because there's 6 of them overall, that way we can modify that at that point. So MSHandle. Now for that one, we're basically just going to fill it with zeros. And then we are also going to just set both of the TX state and RX state to periph inactive. Alright. Now, don't think we need to do anything else in the constructor just yet. Chuck a destructor in there. And then let's just start laying out some of the method declarations we're going to need, and then we'll chuck the code for those into the actual UART.cpp file. So what do we want? We're not going to do that one just yet. We'll come back to that. Okay, so and this will be our initialization methods. DInit, DeInitialize. We're going to want a way to be able to find out what state we're in, so that if we try and initialize, we can check and see whether or not it has actually worked. Let's just call that GetState for the moment. And that will be void. Oh, so we might actually want to be able to retrieve the handle, so this UART handle type def. We're going to want to retrieve that because we're going to do the interrupt handling in our actual serial class, which will kind of sit on top of this driver class. So it's going to need access to the UART handle type def in order to be able to do that. And rather than making that public, which we could also do as another option, I might actually just go that def. Now, we could pass a pointer to that, but we might actually pass a reference to that instead. All right, so it's kind of, let's put a note in here, because these are our constructors and destructors. Let's just call these our initialization methods. We'll call the next slot our control methods. And again, comments just to help break it up a bit, just to make it a bit more readable when we're going through it. So we're going to want to pop in some methods to be able to start and stop the TX and RX interrupts. We're also going to want to be able to retrieve whether or not those TX and RX interrupts are active. So we've got 3 different peripheral states we've put in here. So this one is going to be keeping an eye on whether the device has been successfully initialized or not. These guys will be keeping an eye on whether transmit and receive are actually active. So we'll pop this one in. This will be a void method, yeah. And stop TX. And let's go, so periph state, and let's go get TX state. That will work for that. Now, although I am referencing other code, I'm kind of modifying it and changing it and stuff as I go. It tends to be just the way I do things. I basically never write things the same way twice, because I always find slightly different ways and slight improvements and things that I want to throw in there. So it's kind of partly copying code, but partly doing it from scratch as well. Now, let's go with that for the moment. Now I'm going to leave the constructor and destructor in the header file for the moment. We may end up moving those out to the CPP file. For the moment, we're just going to go with these guys. Chuck those over there. And these are QAD UART initialization methods. Grab that, I'm going to pop that there. And this will be QAD UART init. Now, same as what we did with the GPIO driver, these guys that are returning a periph state enum, we also need to pop that guy in front of those because they do belong to the QAD UART class. So in order for the compiler to recognize what we're actually talking about there, we do actually need to let it know that periph state is a member of that class. So let's go through and get this all sorted here. Okay, let's just delete that bit because that way we can copy and paste this thing like this. That is get RX state. Actually, I should have fixed that up too. These are actually control methods. All right. And while I am looking forward to actually doing some recorded and edited videos for this sort of stuff as well, I do enjoy the fact that on the streams you're actually getting to see everything. I'm not cutting out the boring bits like this, so if anyone's interested sort of the particular approach I take, you'll actually get to see that. Rather than us just throwing in like a montage or something if we were editing it after the fact. Alright, that's all of those guys done. Now the most chunky part of this whole class is going to be the actual initialization part. There's a few things we're going to have to do to be able to determine which UART we're initializing and set up the particular things for that. Because of the way the HAL is written, there's kind of no neater way to do it that I've come across. Someone else might be able to find one, but I haven't myself, unfortunately. All right. Now what we might do is we might chuck another private section in here. And QA results. And we're going to call this peripheral. So we're just going to create a private initialization and DeInitialization method. It's going to allow us to separate out a couple of things. And also, as far as the DeInitialization, there's a point in the initialization process where if it fails, we need to deinitialize some of the stuff that we've already initialized in order to make sure things fail gracefully. So it's going to be a little bit easier if we pop in a couple of private methods here to handle that for us. And for that, we're also going to pop this in private, perif DeInit. So we need to know for our deinitialization method whether we've got to partially deinitialize, as in there's been a failure during the initialization process, or if we're fully deinitializing it. So we've set it up successfully, we've used it, and then we want to shut it down again. So to do that, let's call this DeInit partial. It'll be for our partial deinitialization, and we might make DeInit full for our complete deinitialization. All right. And we may as well make that a void and perif DeInit, and then this will also need a, what do we call that? Perif DeInit, cool. And we'll call that DeInit mode. So we might change that up here too. I like that name better. So it can be DeInit mode. And we'll pop these ones in our CPP file. Just for consistency, we're just going to pop in there that that is a QAD UART control method. Like that. We'll pop these guys down here. QAD UART private initialization methods. Also need to pop that in there. Need that there, and that will be DeInit mode because we changed the name of that. So we need to update that here as well. It's one less error we're going to get when we go to compile. Now I like to add a little bit of extra lines at the end of the file as well, just so that if I go to scroll, I can get where I'm working on into the middle of the screen. Again, maybe I'm just weird like that, but I find it useful. get a UART private initialization methods, like so. Wonderful. Now, for this one, there is actually music. That's why I'm slightly going along with it. I like having music when I code, and unfortunately, even though I had permission to be using the music that was in the first stream, apparently Twitch didn't like it so much, so unfortunately means that I'm listening to the music and not sharing it. This tends to help my brain function a little bit better. This will be perif init. Don't need to pass that anything. I have to remember which one of my code bases I'm actually working on. The other one that I've got up here is actually Crystal Arc rather than Quartz Arc, and it was just me testing out a bunch of things that I wanted to try for these streams. So that's why you'll see me type QA occasionally, because that's CA instead of QA. That's what's going on there. Alright, so if we've gotten to this point, everything's working, so ME state will be perif active, and at that point we can return QA OK. For our DINIT, if we're not initialized, then we will return, we'll call perif DINIT, and this will be DINIT full, I'm pretty sure we called it. We will make our state inactive, and I'm not going to be returning anything. That's all we need to do in there for the moment. Wonderful. This one's a nice easy one because we're basically just going to return ME state. Another easy one because we're just going to return, let's do it this way so I can actually reference what I want as we go. Alright, so we're going to want MSHandle. Excellent. Alright, so these guys we are going to want so you can use, where are we? LDriver Inc. UART. There is these methods in here, the Hal UART transmit IT and Hal UART receive IT, which allow you to do interrupt based transmit and receive. I find it a lot more flexible not using those. So rather than that, we're going to be directly calling Hal UART enable IT to enable our transmit interrupt, passing it the handle and which of the IRQs we are actually enabling. So in this case, TXE, which is basically triggered every time the TX data register becomes empty. It's basically going to ask for more data. So that's what that one is for. And then this will be TX state. Yep. Was perif active. And then this will be basically disabling it. And we'll do basically a similar thing for the receive as well. UART IT TXC METX state equals perif inactive. Now this one is just going to return our ME_TXState. Hal UART enable IT. And the one we're going to go with here is UART IT RXNE, which becomes triggered every time there is data sitting in the RX data register. So letting us know that we need to pull data out rather than putting it in with the TX interrupt. Okay, cool. Oops, that'll be disable. That one, ME_RxState equals periph inactive. And this one will just be returning ME_RxState. Alright, this is going to be the one that has a lot of the stuff in it. So let's firstly throw some stuff into a setup.hpp file because we need to know which pins we are using, which GPIOs, what their alternate functions are. We're also going to chuck the baud rate and the TX and RX FIFO sizes in there as well. Bit of a fan of having this setup.hpp file just so that we can come in and edit a bunch of the different settings all in one go. And actually, while we're in there, we are also going to pop in our interrupt request priority for our UART1 peripheral as well. So as far as our priorities, it's a number between 0 and 16, or 0 and F in hex, where the higher the number, the lower the priority of the interrupt. So in this case, we're just going somewhere kind of in the middle. We will have stuff that's higher priority and stuff that's lower priority. So again, if we put all our priorities in one place in the setup file, as we come to rearrange them and stuff as we need to, we can do all of the priorities in one place, which I think makes it much easier. So just going to go with a little bit of copy and paste stuff just to make it slightly easier. Alright, and all of those are correct. Now, the other thing I do in here, set up the TX pin fairly similarly to the way we did the GPIO. The one exception that we're actually throwing in our alternate function as well. With the RX pin, I do like to use the pull-up resistor. The reason for that is because the start of a transmitted byte is the start bit is actually signified by the signal going low. So as long as the signal stays high, even if you've got nothing plugged into it, it's not going to get a random trigger. If we went with no pull here and we had it set up to a UART that's just connected to pins rather than the ST link like we're going to be using for this one, you can get the pin floating and you will get spurious activity on that pin, which can make the peripheral think that there's actually a start bit when there's not. So just to prevent that, if we pull the pin up, we're going to be fine. Alright, now basically you're going to chuck in a switch statement. So for each of the UARTs, we need to enable its clock specifically. We also need to take note of which IRQ we're actually working with, so depending on which of the peripherals we're going with. So we've got all 6 of them set up in here. For this one, we'll get rid of that final one. So basically just going through enabling the clock for the peripheral, just going through and resetting it, setting the IRQ, and then in our UART handle type def, we're setting which actual UART or USART we are using for that peripheral. So doing it with the switch statement was sort of the neatest way I could find at the time. And that. Right, cool, that all looks good. Next bit we're going to do is actually getting the peripheral itself initialized. So just going through and setting the baud rate based on the initialization structure that we've been handed. Setting up the word length to 8 bits. You can go with 7 bits, 8 bits, or with the STM32, I think most of the range. You can actually go with 9 bits as well, I believe, if you've got parity disabled. So we're not going to be using parity, 1 stop bit. We're going to be doing both transmit and receive. No hardware flow control. We're going to go with 16 times oversampling and turn off our 1-bit sample there. Now, as we can see here, if this initialization actually fails, it's going to go through and do a partial deinitialization down here, which is basically just reversing the stuff that we've done up to that point for the initialization. So turning off the peripheral clock for that peripheral and setting the pins back to default state. And assuming that actually works correctly, then we are going to go through and enable the peripheral. So, and that is just being passed the handle, so it automatically knows which peripheral it's enabling. We're also initializing the interrupt request for this one as well, and taking the interrupt priority that we provided in the initialization structure, and then just enabling the IRQ. So this has basically got everything ready to go, so that when we actually go to enable either the transmit or receive interrupts, it's going to do what we need it to do. So we'll actually get interrupts being triggered as need be. Now, if we get to this point, then everything is properly initialized, which means we are going to return QA OK. And we'll just get our deinitialization stuff sorted as well. And again, just going to copy and paste this because I like the previous code I came up with for this. And then I'll sort of explain what we're doing. So similar to what we did before, I'm just going to go through if it's a full deinitialization, then we're going to go through and stop the TX and RX interrupts, disable the IRQ, so opposite of what we've done here, disable the actual peripheral, and then get the HAL to deinitialize it for us. And then we'll go through using the switch statement and disable the particular clock for whichever peripheral we are actually going with there. And then finally, just going through and deinitializing our RX and TX pins, so that by the time the deinitialization is done, everything's the same as it was before we actually tried to initialize the peripheral. Now, that all looks fairly good there. All right, let's see if that will actually build. Doesn't look like it. 25 errors. Stuffed something up pretty good there. All right. we want how to do it in here. GPIO type def. Ah, that's why. It should be type def, not init def. Alright, that's those ones. What do we got here? Got a UART perif. It should be kill. Spelling mistake. Wonderful. And what do we got here? What do we call it? Okay, so that's giving us an error because there's one up there, so that's fine. That should be MU baud rate because it's an unsigned integer. And then the errors are there because we had our GPIO type defs incorrect, so that's those ones. And that should be a queue. That would help. It's this one. Okay, cool. Cool, it's got both of those gone, and I'm guessing there's a few in here too. Of course there is, because we've copied and pasted code. So let's just do a find and replace. We're going to go CAD, we'll replace that with QAD. And I'm guessing that should sort out most of those. What we got there? Because we actually called this one perif DInit. Cool. And that should be QA fail. Cool. No errors, no warnings. Now, how long's this stream been going for at this point? Okay, cool. So what we might do is get the FIFO class done and then call it an evening. It's getting rather late in my time zone. And I wouldn't mind grabbing some sleep because I have a friend's birthday party tomorrow. So we're going to go with creating another folder. And we're basically going to create a folder just to put various tools in. So a FIFO buffer is something that we can use for a whole bunch of other things, not just for the UARTs. So we'll create a tools folder to pop stuff like that in because it's kind of universal. And of course, because we've created that folder, we're going to have to go in here and set up our include and source paths for that one. So that will be QA tools. Excellent. And source location. Pop that one in there like that. Yes. Cool. And I'm going to create header file. Let's just call this QA FIFO. So I think that's the only thing we're going to pop into these files. And always come back and rename stuff if we need to at a later date anyway. Alright, cool. So we're going to grab our header out of here. It nearly even named it the way I would have. That's brilliant. Not a fan of those templates, they're kind of annoying, but okay. Definitely going to want to include setup in there. Actually, this is going to be QAT FIFO. I haven't stuck with my preferred naming scheme for this one, so we're going to have to fix that up. So QA for Quartz Arc and NT for tools, because that's the system that this belongs to in our code. And this will be FIFO buffer. Right, cool. And it's actually the 25th now. It wasn't the 25th when this stream started. Okay, cool. That all looks good. We do need to fix this up though. So that'll be QAT, and same for this one here. No, wrong one. It moved the file on me. There we go. Awesome. Chuck this in here. We'll get rid of this recursive inclusion stuff for this one. This is going to be including QAT FIFO. Get rid of that stuff. And this is the CPP file for that one. Alright. So this will be QAT, let's call it FIFO buffer. So create a class for that one. QAT FIFO buffer. So if you never come across a FIFO before, it basically means first in, first out. So the first bit of data that goes into the buffer is the first bit of data that gets pulled out. So say in the case where we're receiving bytes via serial, those bytes will be read out of the buffer in the same order that they go in, rather than sort of what would happen in the case of, say, a stack or something like that. Alrighty, so we're going to need, just like the GPIO driver and the UART, our default constructor we're going to delete, because in order for this to set itself up, it's going to need to know how big it needs to be. So for that, we're going to pass it a uint16t, and let's just call that usize. We are also going to store our size in here, so mu size, just so that we can retrieve that if we need to. And a couple of different ways we could do the actual buffer. We could use a string, we could use a vector, we could use a raw C pointer. However, I think what we're going to do in this instance is actually use a C++ unique pointer, because the FIFO buffer itself is the only thing that's going to be accessing that pointer. It'll be passing bytes and receiving bytes, but it's not going to actually hand its pointer to its buffer to any other class or any other part of the code. So we use a unique pointer for that, just because it tends to be a little bit safer. So in order to do that, we're going to have to include memory, and then we'll go with standard unique pointer. The template for that one will be uint8t, because it's just going to be a single byte, and then mp buffer. And we'll line those guys up just because it looks neat. So where are we? What tools? There we go. Alright, just making sure I'm not forgetting anything. So we also want to keep track of our read index and our write index. And these will keep track of where we're up to in our buffer. So the buffer will be treated circularly. So it'll start from the start, fill it up with bytes. Once it gets to the end, it's just going to wrap around and keep going. So we're going to keep track of where the write index is for the bytes coming in and the read index for the bytes going out. And the cool part about doing it that way is, for the most part, if the read index and the write index match, then there's no data waiting in the buffer. If they don't match, then there's bytes waiting. So I kind of like that approach. So let's initialize this. So MP buffer, we're going to go standard make unique uint8t. Actually, that should be an array. Otherwise, we're just going to create a pointer to an individual uint8, and that's really not going to do much buffering for us. Alright, that should do that for us. mu size, that will be usize. Oh, actually, I need to pop usize in here as well to let it know how big to make that array. Mu read index will be 0, as will mu write index. Alright, that's all we need to do there. That all looks good. Stream still behaving itself, that's also good. Alright, now, whereas if we did like a C style pointer, we would actually need to delete the buffer in the destructor. So allocate the memory in the constructor, deallocate it in the destructor. However, with the unique pointer, it actually keeps an eye on when it falls out of scope. So as soon as it falls out of scope, C++ automatically gets rid of it. And unlike a shared pointer, or can't remember the other pointer type off the top of my head in C++, but the unique pointers don't really carry too much overhead. So not really a problem with doing it this way. Now we might actually code all these methods in the header file and then move them across, just because we can see everything in one go while we're actually coding. Now, this method will be used to actually clear the buffer. We don't actually need to worry about clearing the array. The data can stay there, because as long as we set our read index and write index both to 0 or even just the same thing, then the buffer's effectively going to be empty. We're also going to create FIFO state. This can be a uint8t. And let's call this fs not empty and fs empty. Create a method so that we can check how much data is actually pending. Oops. mu write index. Now, because the buffer is circular, at some points the write index may be greater than the read index, which is kind of the normal state prior to it wrapping around. However, there will potentially be a situation where the write index is wrapped around and the read index hasn't wrapped around yet. So we also need to account for that when we're figuring out how much data is sitting in the buffer. So now the other thing that we've done here is we've read the write, that sounds confusing. We've read the write index into this write index variable rather than just accessing it directly here and here. The reason for that is because there is potential for a situation where an interrupt request has been triggered. In that interrupt, it may have put data into this particular FIFO, and if it's done that, say, in between the instructions for that and the instructions for this, it's going to mess things up a bit. So this way we're only pulling one copy of it, and we can't end up in a situation where it's going to mess up things partway through. Kind of got to almost think of dealing with interrupts kind of the way you deal with multiple threads on, say, a traditional computer, so that stuff doesn't interfere, which is something I find slightly fun. Now in this case, because write index will actually be less than read index, we need to figure out not the difference necessarily between write index and read index. We need to figure out the difference between read index and the end of the buffer and the start of the buffer to write index, and add those together, because that gives us how many bytes are actually pending in the buffer. Like so. So if we're in a situation, normal situation, where write index is greater than, this should be mu read index, like that, then it's just a matter of going write index minus read index will tell us how many bytes. But if write index is wrapped around and read index hasn't yet, then we need to do this in order to figure out what the correct number of pending bytes in the buffer are. We're also going to pop in a push method to push data onto the FIFO. We'll need a pull method to pull data off the FIFO. Actually, that should be push and pop. There we go. That's better. MP data mu write index equals u data. So basically just putting the data that's coming into this function onto the buffer at the particular write index that we have, and then we need to either increment or wrap around the write index once we've done that. So less than or equals, it'll be mu size -1 in order to make sure we don't have overflows. Actually, we're just going to go, that will be mu write index plus losing my voice, and this will be mu write index equals 0. Cool, that looks good. Now this is going to actually check to see if the FIFO is empty first, because there's no point us popping data off and messing up our read index if the FIFO is actually empty. So let's chuck a method in here. We'll call that FIFO state, I think. Yep, cool. FIFO state, let's just call it empty, make that a void, and this one is just going to return mu read index equals mu write index. So if these guys are equal, it's going to return fs empty. That should be a question mark, and this will return not empty if then not equal. So this can then use that down here. So if it's not empty, then I'll grab a copy of the data at the read index. And again, we need to either increment or wrap around the read index depending on where it is. So this will be mu size -1. So this is basically the same as what we do with the write index. Like so. And the last thing that we need to do there is actually return the data that we just pulled out of the buffer. And then if it is empty, we're just going to return 0. And that is basically our FIFO. Now, what we might just do is grab hold of this stuff, and we're going to move that over to our CPP file. And this will be QAT FIFO. Let's just call these data methods. QAT FIFO clear, and it will be QAT FIFO data method. Might just grab that guy first up and fix these up, just so the compiler knows what we're actually talking about. Might help if I put it in the right spot. So this is basically all we're going to get done for this stream. We will look at finishing off the serial driver during the next stream. However, if you're curious about any of this code, want to have a bit of a closer look at it, I will put a link to the GitHub in the description on the YouTube channel and in the description on the Twitch channel as well. So that'll be there so that anyone can download it. Not that it's doing too much exciting just yet, but things will start to get a little bit more fun after the next stream. A lot of these first 3 streams has just been getting sort of the groundwork and foundations laid for us to start building everything else on top of. Unfortunately, it does mean sort of getting some of the more boring stuff out of the road first up. But I also personally think it's some of the most important stuff, and anyone who has spent the 2.5 hours to sit through the very first stream, there is so much useful stuff there as far as just generally making your life easier and having more of an understanding of the STM32s and cube IDE and stuff like that. Alright, so these are These were data methods, I think I called them, so we'll keep that consistent. And these guys are constructors and destructors. Alright, let's see if we got any errors there. Yes, we did. Alright. None in there, which is good. What's this complaining about? We called it QAT FIFO buffer. Of course we did. Alright. So QAT FIFO buffer. That might work a bit better. See if that compiles. Alright, what's... that should be... Actually, it should be m_p data, which means I've not named it. It's actually buffer. Logically. There we go, fix that one up, and we're going to need to fix that in here. That should solve that problem. Wonderful, 0 errors, 0 warnings. And I'm not actually going to even chuck this onto the discovery board at the moment because it's not really going to do too much yet anyway. However, by the end of the next stream, we will have some stuff set up so that we can actually be sending text and data back to the computer so that we can start to test that. And then either in the stream after that or one of the other upcoming ones, then we will be looking at setting up the console or terminal system that I was talking about, where we can actually have commands and stuff like that. There's a particular approach I like to take to actually parsing the incoming strings, which allows it to sort of break those up really easily so that we can go through and process those and create our own methods to be able to convert elements of that string into integers or convert it from hex and things like that as well. And that all looks good there. Pretty happy with that. Close that file. So to anyone that got this far through the video, thank you so much for watching. I actually really enjoy doing this anyway, so even if I wasn't streaming and putting it up on YouTube, I'd still be sitting here doing the same thing. Probably not talking quite as much, but hopefully some people find this entertaining. If you do, please follow me on Twitch, subscribe and like on YouTube. There is also, let me grab that one, because down the bottom left there, you'll actually see the subreddit. I post links to all of the streams and videos and stuff on the subreddit, and it's a place for people to come and ask questions and things like that if you're curious about any of what I've been doing. If you want me to go more into depth into explaining certain things, definitely ask. Kind of just having a bit of fun here, so I may have glossed over certain things that some people might want to understand a bit better, and I'm happy to try and explain that. There is also the GitHub address, which I'm going to pop in the description anyway. as well as the Patreon. So although a bunch of the code that we do through the first few streams is going to be freely available, any of the more advanced stuff that we've got coming up will be available on GitHub to Patreon members. As much as I would love to be able to give all of the code away for free, do have to pay money to keep the lights on and pay for internet and all of that sort of stuff. So in order to keep doing this, it's kind of, if people support it, it's going to allow us to do better things, set up a better streaming setup and all of that sort of stuff, so that we can make it more fun for everyone. There is also the email address there as well, the onesandzeros.contact@gmail.com. So if you don't want to jump on Reddit and leave a comment there or message me there, you can also send through an email. I don't check that as regularly as I check Reddit though, so if you don't get a reply to that straight away, that's why. So yeah, thank you so much for watching. There will also be improvements, as I mentioned, to some of the setup coming next week, so looking forward to that. And hope everyone has a good night or good day or whatever it is where you are. It's like 1 in the morning here, so awesome. See you later.